And we are live, okay? جاهز أبو يوسف؟
يلا بسم الله.
يلا بسم الله. So, Assalamu alaikum and welcome to another seminar from the Computer Engineering Department at KFUPM. Tonight we have with us Dr. Mohammed Flimban, and he's going to speak to us about quantum computing and the transition from classical to quantum computing. Dr. Mohammed Flimban is an assistant professor in the Department of Computer Engineering. He joined the department in 2018 after he finished his PhD. He obtained his PhD degree from Purdue University. He also obtained his master degree from KAUST. Dr. Flimban is also has a Bachelor of Science from the Department of Computer Engineering at KFUPM. He obtained the degree in 2008. He has been currently appointed as the director of the Center on Intelligent Secure Systems. He's also teaching several courses on quantum computing at the undergraduate and master level. Okay, Dr. Flimban, you can take it over.
طيب بسم الله الرحمن الرحيم. Thank you, Dr. Yahya, for the introduction, and I would like to welcome you all for this talk. And I would first of all, I would like to give you some set expectations about this talk. So this talk will be basically just a barely introduction to the quantum computing field, and I will do that through by taking you through a journey from the classical computing to the quantum computing, and what is so we will go into the why do we care about quantum computing and how does it really work, and basically we go into the definition of quantum computing, and basically we'll go into a little bit of the state of the art of quantum computing nowadays. So basically, so let's just start with the why. So computing has been, we know the concept of computing since the early ages. Basically, it started by the Chinese and the Greek by using the abacus, which is the basically primitive form of calculating, and then we have the sliding rules, and then the concept of computers did not come into light until the 1800s with the mechanical computers. So in around the first decades of the 1800s, the humanity saw the first mechanical computer that was called I think the analytic machine by Charles Babbage and with the help of Ada Lovelace. But then in 1900 we have seen this revolution of computing with the introduction of resistors or transistors. So we have the first electrical computers, the ENIAC in 1940s, and then since then the rest is history. Nowadays we have laptops and mainly computers in the palm of our hands. So this evolution of computers, classical computers, has a backstory, and the story really goes into is the transistors. So about 1910s or so, we had the first kind of transistor, which is the vacuum tube. Basically, it's a way to control the current, whether it's that we allow the charges to flow or we stop it. And then with the advances of science and engineering, humanity were able to reduce the size of transistors until we, nowadays we have millions, if not billions of transistors in a small integrated circuit. And we are touching, the physical limit of the transistors, and we are going even below the nanometer scale. So this phenomena of reducing the size of transistors, we know of a law. It's not really a scientific law, but it's more like a prediction. We call it Moore's law by Gordon Moore, the co-founder of Intel. Like in 1970s or so, he predicted that the number of transistors in a confined area will double every 12 months, and then later it was refined to 18 months, and now the rule is or the law is that the number of transistors double every 2 years. Now, see, this is the kind of the evolution of the number of transistors, okay, and that is basically by reducing the transistor size. So in the 1999 we had 180 nanometers, and in 2020 I think Intel announced reaching the 5 nanometers. Now, as we go smaller, the transistors go smaller and smaller, scientists and engineers starting to see or to observe some weird phenomena. And basically they started to observe that the particles disappear from one place and appear in another place, okay? And this phenomena is called quantum tunneling. And that is because we are reducing the size of transistors to the scale where classical physics do not work anymore, and we start to observe the quantum physics laws, okay? So now, this is one side of the story. That is, in terms of classical computing, we are reaching the physical limits, and probably that is the time to think about quantum computing in order to increase the computing capability. But I don't want you to think about quantum computing as the natural replacement for classical computing. In fact, classical computing will be there, will still be there for the next, I say 10, maybe 50 years, just for the reason that for the time being, quantum computers cannot work alone. It has to have a controller that is in a phase or in a form of classical computing. But the other part of the story that I want to tell you is that, in fact, quantum computing or quantum computers, because of the quantum physics the quantum physics laws that it uses, it can do things that classical computer cannot do. And I would like to explain that with a very simple example. Okay. Now, suppose that we have a black box. Suppose that inside this black box there is a painting machine. Okay. So that we roll inside this black box a ball. And depending on the configuration of this painting machine, it will repaint this ball either with a white color or a black color, okay? Regardless of depending on the color of the ball. So assume that we have, let's say, 2 balls, one black and one white, and we roll it inside this black box. Now, depending on the configuration, okay, it will either take a black ball and just pass it as is, meaning it will paint it as with black color. It will take a white ball and again paint it as white. Okay, so the configuration of this painting machine basically will leave the color as is. Now another configuration could be take a black ball, turn it into white or paint it as white. Take a white ball, paint it as black. A third configuration could be take both black ball and white ball, produce it as black balls, okay? The fourth configuration can be taking both balls, produce a white, or paint it as white with white color, okay? So we have 4 configurations of this black boxes, okay? Now, we would like to, generalize this and make it a little bit in abstract. So the way we're going to do it is, rather than using black and white balls, we're going to use bits, 0 and 1. So in fact, if we, so let us say that a black ball is 0 and a white ball is 1, and the output can be either, a black ball or a white ball, depending on the configuration of this black box. Now, from the previous slide, we can identify 2 types of these configurations of these black boxes. Red boxes that produces either zeros, both zeros, which are like black balls, or ones, like white balls. Okay, and we have the black boxes, which basically take the ball as is, right, and take the ball and produce it as is, or it will flip the color. So a black will become a white, and a white become a black. A 0 becomes a 1, and a 1 becomes a 0, right? So we have 2 types of configurations or black boxes. We have a constant configuration, and we have balanced configuration. Constant because the color of the balls are the same, and the colors of the balls are the same. While balanced, we have 2 colors, right? One white and 1 black color. Now the question that we have is, without knowing what is the configuration of this black box, of this painting machine, can you tell what is the configuration, whether it's a constant or balanced? Meaning, if you roll a ball, whether it's white or black, can you tell me with confidence what is the output? Is it going to be a white or black? And in order to do that classically, first we need to roll in black balls into the four boxes. Now, again, we don't know what are the configurations of those boxes, right? And then we observe the output. So in the first box, we will get a black ball. In the second box, we will get a white ball. In the third box, again, we get a black ball. In the fourth box, we get a white ball. Now, using one ball as input will not tell us much, because the output could be black or white, right? So we cannot say whether this box is constant or balanced. Okay. So in order to make sure, to assure that, or to make sure that, with confidence that we say that this is a constant or balanced, we need to roll another ball. Okay. So first we roll a black ball. Now we're gonna roll a white ball, and then we observe both outputs. So now we can tell that this is actually a constant. Again, this is a constant because we have 2 colors. Now, if we in this box, we have black balls. So no, we know that these are constant functions. Okay. So, in other words, or in conclusion, if we think about these boxes in a classical sense, we need at least 2 evaluations, or we need exactly 2 evaluations. Okay, so we need 2 balls and check the output of those 2 balls. Okay, now what quantum computing does for us is that we have proven that we can do that in a single evaluation. So just one evaluation. Okay, so what can that result is was in 1985 by a scientist called David Deutsche, and that was a remarkable result, and that kind of gave hope for the quantum computing scientists that quantum computing can actually solve the things classical computers cannot do if we have a quantum computer. But now I told you that quantum computing can actually, with confidence, with 100% confidence, that say that this box is constant or balanced with just one evaluation. So actually we reduce the number of evaluations from 2 to 1. Okay, so almost by half. So one say that, okay, so what is although this is the kind of remarkable result, but it's not significant, right? Because we're reducing just one evaluation. So it took about 4 years to prove or to generalize this concept. Okay, and in order to generalize this concept, rather than taking or inputting a single bit, we're gonna enter to this function a string of n bits. Like for example, if we have n is equal to 3, we will enter 0, 0, 0 or 0, 0, 1 or any other configuration. And for the output, okay, it will either output 0 or 1. Now, using the similar concept from the previous slide, we can actually have two types of functions. Okay, constant functions, regardless of what are the inputs, will always give us a 0 or will give us a 1. Okay, regardless of the inputs. So, for example, in this column here, whatever numbers or whatever configuration or whatever string that we enter to the function, we always get zeros. So this is an example of a constant function, or constant box. A balanced box, on the other hand, will give us zeros for exactly half the inputs and ones for the other half. So this is an example of a balanced function, the column on the left. So if you see, for example, 0, 0, 0, the output of this function with this input is 0, while 0, 0, 1 has input 1. But if you look carefully, there are 4 inputs that produces 0 and 4 inputs that produces 1. So this we call this balanced function. Now the question is again, how many evaluations do we need, right, to say that whether this function is constant or balanced? And it turns out you really need about 2 to the power n minus 1 plus 1 evaluations. Okay, and that is basically, sorry, I think there is something wrong with the animation. That is basically by checking all possible configurations. So when n is equal to 3, there are 8 2 to the power 3 or equal to 8 configurations, right? So really we need to try them all. Now, if we get lucky and we have this kind of function where it assigns 0 to 0, 0, 0 and 1 to 0, 0, 1, so we need 2 steps, right? So we need 2 evaluations. We evaluate the first line and we get a 0. We evaluate the second line and we get a 1. But we have been told that this function will give 0 for half the inputs and 1 for the other half. So once we get a 0 and a 1, immediately we know that this is a balanced function. But if we get unlucky and we have this function, right? So we need to kind of, using brute force, try all configurations. So we'll try the first one, it's a 0. We'll try the second one, it's a 0, right? So again, we don't know at this point whether it's a constant or balanced. So we have to try the third one, 0, 1, 0, we got a 0. 0, 1, 1, we get a 0. Now we reached half the number of configurations. Now this is where you kind of make sure that the next evaluation, if it's got a 0, that's a constant. Otherwise, that's a balance. So in the worst case, you need half the number of configuration plus 1. So in this case, if you have n equal to 3, then you need 4 plus 1, which is 5 evaluations. And that's in general 2 to the power n minus 1 plus 1 evaluations. Now, so as I mentioned, so this is kind of a generalization of the previous problem, Deutsch problem. Now this problem is called Deutsch-Jozef problem, where they were able to reduce or to show that in quantum computing, we only need a single evaluation, just a single evaluation. Now this is remarkable because we have almost an exponential reduction in terms of the number of evaluations, right? So this is why really quantum computing is kind of an emerging field and kind of one field or one computing paradigm that has a lot of potential because of this kind of reduction in the in computation. Now let us go a little bit into the how. Okay. Now, one thing that I didn't mention in the beginning of my talk is that this is purely from a computer science and engineering perspective. So I'm only going to use exactly 2 slides that contains some physics background. And this is the first one. Okay. So rather than I explain what is happening, or what is quantum, the kind of one important experiment in quantum mechanics and quantum physics, which is the double slit experiment. I will just let you watch this 2 minutes video. Okay, so the conclusion of this video is that, so this is, again, one of the most important experiments in quantum physics, which laid the ground for many other discoveries, is that, you know, or photons act like waves, and waves, of course, they have this phenomena of interference, right? So as you have seen, when you project the waves onto the wall and the back, we have some regions with high intensity and some with very low intensity. And the remarkable thing is that if you shoot quantum objects, okay, then the quantum objects will also behave like waves, meaning that there in the back wall there will be some regions with high intensity and some regions with very low intensity, right? Pretty much just like waves. So again, I'm not going to touch or not going to tap into the physics of it. I'm going to tap on the kind of the mathematical model for that. And I would like to take a quote from this book, Quantum Computing Since Democritus, by Scott Aronson, which is one of the pioneers in quantum computing. He's from computer science background. So he says that, you know, quantum mechanics is what you would inevitably come up with if you started from probability theory. And what he said is to generalize the number that we use to call probability to be negative numbers. As we know that probability is, you know, positive numbers between 0 and 1. So if we could replace that with negative numbers, right, then we'll be able to model this interference phenomenon, right? And then he continued, he said that this theory could have been invented by a mathematician or computer scientist. In one of his lectures, he even said, you know, computer scientists could have developed this theory of quantum physics. And I have attended few of his lectures on YouTube and personally. The very first thing that he, in one of the lectures, he started with, you know, saying, and I'm quoting his words, that physicists are fooling us by telling us that quantum computing is actually a hard topic, while it's actually, you know, easy to digest topic if you know linear algebra. And indeed, there are some background, some minimal background, like basically in linear algebra, that then you actually wrap around your or kind of digest the concept of quantum computing. But for now, let me tap into this idea of replacing probability with negative numbers, and I will do that way using a very simple experiment, okay, or a very simple model. If we toss a couple of coins, then we have 4 possibilities, right? Depending on the output of those 2 coins. So we either have 2 tails, 2 heads, a tail and a head, Actually, we have either a tail and a head or a head and a tail. Now, if we want to find the probability of getting exactly one head, right? That is one half, because the probability of getting a tail by the first coin is half, and the probability of getting a head by the other coin is exactly one half, right? So if we kind of add up or sum up the probability of those two events, then that's one half. Now, if we replace these numbers with some other numbers, okay, some negative numbers, we will call it complex amplitude. And don't worry about the assignment; these are just kind of arbitrary assignment. But see what is happening here is, if we calculate the probability of getting one hit, that is equal to 0, right? So now, using complex amplitude concept, we can actually model the interference property of waves and quantum particles using complex amplitudes, and that's the first concept that we learn whenever we start talking about quantum computing. The other important concept when learning about quantum computing is the concept of superposition, and that is kind of a unique or a feature that only appears with qubits. Like in classical bits, that it represents any binary system. Like, for example, a light bulb that is on or off can represent either 0 or 1. We can also represent a 0 and a 1 using high voltage or low voltage, or you can also control it with transistors, right? In the equivalent unit in quantum physics or quantum computing is called qubit, okay? And again, similarly, we can actually model the 0 and 1, the binary system, using an arrow, okay, that is inside a 2D circle. If the arrow is pointing up, right, we call that qubit in a 0 state, and we represent it using this symbol. And I'll explain this symbol in a minute. Now, if the arrow points down, that's a qubit in the 1 state. Now, I always, like I used to, whenever I see this weird symbol, I get a mental block and I start, I basically stop reading whatever that is in my hand. But until I learned that, this is just a shorthand for a column vector. Okay. Obviously, this is in its basic form. So a 0, like a qubit with a state 0, is nothing but a column vector that looks like 1 and a 0, and a qubit state a qubit with a state in the 1 state is nothing but a 0 and 1. So this symbol is called a ket. So this is a Dirac notation put by Paul Dirac, and there is also the bra, which is the row vector. Now, what is superposition? See, in classical bits, we can either have a 0 or a 1. We can either have a high voltage or a low voltage. We cannot have both in the same time. But in quantum computing, in qubits, we can have the qubit, okay, in many other, or in the same position at the same time. So I said that the qubit be in the 0 state if the arrow is pointing up, and 1 state if the arrow is pointing down. Again, so this is kind of in a simple form. But what happens if the arrow is pointing towards the right? Now we call it in a superposition state, and basically it can be in any angle over the 360 degree in this circle. But this is what is called the superposition state, because the qubit will be in both states, 0 and 1 at the same time, with complex amplitude of 1 over square root of 2. And the way we read it or we see it is that this qubit is actually in both states. If we measure it, if we see it, if we kind of capture the information in this qubit, we will get 1. We will see 0 50% of the time, and we will see 1 50% of the time. Okay. Now, I use the word C, but there is actually a technical term for that, which is measure, that I will explain in the next slide. But see, I'm using a 2D circle here, but in fact, we can represent a qubit using a sphere, a 3D sphere, right? Okay, so this is the arrow can point in any direction inside this sphere, and this is a tool to visualize the qubit or the state of the qubit using which is called block sphere. Now, the problem with this qubit is that it will be in whatever state, and we don't know what is the state of that qubit until we have a way to measure it. And if we don't measure it, right, we will not be able to kind of do any processing and any computation on top of these qubits. So measuring is a key operation in quantum computing. But again, measuring is a little bit tricky, because we really need to measure the qubit in certain way, okay? But we don't know, and that way basically is the direction of measurement, okay? So let us assume that we have 4 qubits, one with an arrow pointing right, one with left, up and down. So how do we measure these qubits? Let's assume that this is a measuring device, and we have 2 options for the time being. We have 2 options to measure this qubit. One is to align the measuring device horizontally or vertically. Let us do the horizontal first. If we measure the qubit horizontally, and the qubit were aligned horizontally also, then we will get, let's say this arrow was pointing toward right, then this is 0. If we use a horizontal measure and the arrow was pointing to the left, the qubit is 1, or the state is 1. Now, for this qubit, let's say that we're gonna measure it vertically, right? So if it is pointing up, that is a 0. If it's pointing down, that's a 1. Now, we were lucky because at this stage, we don't know what is inside the qubit, and they are aligned horizontally. And we also align the measuring device horizontally, right? So we were actually the arrow, right, was actually aligned with the measuring device, okay? But since we don't know what are the qubit state, sometimes we measure it in a different direction. So what happened here is, suppose that the qubit is, or the arrow is 0 in the horizontal state, and horizontal direction, and we align the measuring device vertically. So what will happen is the qubit will collapse into the horizontal state. Let's say it collapsed to a 0 state. Again, if we measure this qubit, sometime it will measure down. So sometime we will measure a 0, sometime we will measure a 1, although they were the same qubit state. They were in the same state, except that when we measure it on a different direction, we will get some different results, probabilistic results. Similarly, if the qubit is pointing up and we are measuring horizontally, sometimes we get a 0, sometimes we get a 1, with 50-50% chance. Okay. So again, if we are measuring, if the qubit is horizontal and we are measuring along the vertical axis, we say that, with respect to this vertical axis, the qubit was in a superposition state, so it will collapse either to a 0 state with 50% or a 1 state with 50%. Okay. And there is nothing special about vertical and horizontal. We can actually use any direction, like for example, northeast, or northeast, right? Now suppose that this qubit is state is pointing toward the right, then we have 85% probability that the qubit will align itself to the northeast, and there is a 50% that it's going to actually align itself to the southeast, right? So the probability of the qubit state that we measure depends on the direction and the previous state of the qubit. And that's why measuring is actually a tricky business when it comes to computation. But the nice thing is, once we do the measurement along this axis or along this direction, and the qubit, let's say, aligned itself to that direction, if we measure it so many times, it will give us the same direction 100%, with 100% probability, okay, with one probability. So it always will be in that direction. So this is what in terms of measuring, right? So let us get back into the superposition, okay? And let us maybe try to exploit this phenomena to achieve what is called quantum parallelism. Now, as I mentioned that a qubit or a bit can be, in qubit sense, it can be both in a 0 and a 1 state. So I'll just denote it with this symbol, meaning that it's actually in a superposition state, right? So assume that we have an AND gate, and I'm using AND gate because, so this is kind of the one of the logic gates, AND gate. So and the reason is that we can actually do any arithmetic operation using some basic form of logical gates, mainly AND, OR, and NOT. Or if you want to do the, we can actually represent any arithmetic operation using the universal gate, which is NAND. But nevertheless, you know, like we will try to, I'll try to explain the parallelism using this just AND gate. And you know that AND gate, okay, takes two inputs and produces one output. And the output of AND gate is one only if both inputs are one, right? So if we put the input qubits in a superposition state, and we somehow put it into an AND gate, so it produces an output, either a 0 or 1, with 75% being a 0 and 1% being or 25% being a 1. And that basically represents the truth table for the AND gate, right? Because if you have a 0, 0, we'll get a 0, 0, 1, we get a 0, 1, 0, we get a 0, and 1, 1, we get a 1. So basically 75% of the time will give us a 0, and 25% of the time will get a 1. So now what we did is that we actually did 4 operations at the same time, simultaneously, in parallel, right? And we can actually represent the output using this equation, meaning saying that the complex amplitude for the qubit in the 0 state is square root of 3 divided by 2. We usually square this complex amplitude, so it's going to be 3 over 4, which is 75%. And with 25% or 1 over 4, it will be in the 1 state. Now, okay, great. So that then we can actually achieve quantum parallelism using superposition. But at this stage, we really need to measure what is the output. And once we measure it, we will collapse the state, the qubit state, into either a 0 with 75% or a 1 with a 25%. So now the problem, yes, of course, you know, like at this state, the operations were, you know, executed in parallel. But at the end, in order to measure the output, it has to collapse to either a 0 or a 1. And there is this misconception about quantum computing, is that quantum computers can actually solve any problem using brute force, basically by running things in parallel. And that's kind of false, or a misconception about quantum computing, because at the end, you need to measure. And once you measure, you might get the wrong result. And how do you know that if this is a good, the right result or wrong result? So that's kind of, you know, kind of a contradiction. So basically, quantum computer does not work this way, just basically by putting things, arranging qubits into superposition and running over, you know, like the whatever computation or function, and then, you know, get the output in parallel. Now, again, in order to process or compute useful things out of these qubits, we need more of those logical gates. Now, unfortunately, AND gate, OR gate, NOT gate, AND and OR and XOR will not work with qubits, or will not work in quantum computing. I'll explain in a minute. What work are some qubits or some gates. We call it 1 qubit gates. These gates are of great importance. They are called Polygates. Basically, think of X gate as a NOT gate. Basically, it will rotate the qubit along the X direction. So if we get a x-axis, so if you get a 0 and you apply it to the x gate, you will get a 1, and vice versa, right? Similarly, because we have 3-dimensional sphere, so y gate will rotate the qubit along the y-axis, z gate will rotate it along the z-axis. Okay, so I'm not going to go into the details, but I just want to show you the basic gates that we allow us to compute or to process the qubits. Another important gate in quantum computing is what is called Hadamard gate. And this gate is the one that allows us to get into the superposition. So if you are wondering, okay, superposition is a nice concept, but how do we realize that? So there is a gate called Hadamard gate that exactly does this thing. So take a qubit in the 0 state and produces a superposition state in a 0 and a 1 with probability half each. Okay. Now, as I mentioned, in order for the gates to work with quantum computing, we need them to be reversible. Meaning, if we apply the same gate, right, we will end up with the initial input. So if we have a 0 state, a qubit in a 0 state, we apply it into an X gate, so it will become a 1. And then we apply X gate, we'll end up with again 0. So the net effect of applying these gates is the identity gate. So basically, the initial gate or the initial state will be exactly the same. And this is called reversible gates. Let us think about and or, right? If reversible gates meaning if I give you the output, right? Can you tell me what is the input? So if I tell you that this is an AND gate and the output of this AND gate is 0, what are the outputs? There are 3 possibilities: 0, 0, 0, 1, and 1, 0, right? So this gate is irreversible. The same goes for OR gate, okay? So basically, AND and OR gates, they do not work with quantum computing. We have other reversible gates. One example for that is CNOT. And this is mainly one of the basic and most important gates in quantum computing. And CNOT basically is think about it as an if statement. If the qubit represented by X is equal to 0, then the Y qubit will be the same as the output here is the same as the input, which is 1. Okay. Now, if X is 1, we're going to flip this qubit from being 0 to 1 or from 1 to 0. And this is kind of a truth table, and this is the equivalent circuit or the equivalent function using XOR gate. Okay. So now let us take the output, which is, let's say, 0, 0. If I tell you the output of a CNOT gate is 0, 0, right? We immediately know that the input is 0, 0 because there is no other configuration that of inputs that produces a 0, 0 as an output, right? So this is basically the concept of reversible gates. Okay, and there are many other reversible gates. Basically, kind of a combination of CNOT. One is called CC0, the controlled CNOT gate, and there is a swap gate, and so on. But they all can be, built using a simple CNOT gate and the previous 4 gates. Now, why I'm going into these gates, because we can actually combine them in ways to achieve other functionalities. One important circuit is if we put a Hadamard gate before a CNOT gate at the upper qubit. That will give us, so now we have 2 qubits as input, right? But that will produce both qubits in some unique states, okay, in this state. And that says that, if we have this 2 qubit system, if we measure the first one, okay, and suppose that it's a 1, now the second qubit definitely is a 1. And let's say if we measure it, we measure the first qubit and becomes a 0, or sorry, it used to be 0, now it's a 1. Now immediately we know that the second qubit is is also 0. And in fact, these are called build state. Okay, so this is one of the build state. So in fact, even if we separated those two qubits, right, in the universe, and we measured one, and it turns out it's a 1, we immediately know what is the output of the other qubit. We don't know, but you know, like the qubit, the state of the other qubit will align itself to either the same or the opposite of the other qubit, even if they are far away apart in the universe. And that's what's kind of make Einstein say that, you know, these are actually spooky actions at a distance. So he was not really convinced with this phenomena, and that led him to, you know, put what is called the EPR paradox. Now I explained without you knowing four or at least 2 quantum physics laws or rules that are used to realize quantum computing. Okay, so basically quantum computing, if you go into a textbook definition for quantum computing, it says quantum is a new computing paradigm that exploits quantum physics, mainly interference, and that is modeled by complex amplitude, superposition, and entanglement. Okay. So this is basically a very brief history of quantum computing. And now, quantum computing originated in about 1980s by physicists, namely Paul Benioff and Richard Feynman. But it took about 5 years after that for the very first quantum algorithm, which is the Deutsch algorithm that I explained early in the talk. But again, that problem was not really useful. Okay, so what if we know that a function is constant or balanced? But it is again remarkable, as I mentioned, because it showed that quantum computing has the potential of achieving such exponential reduction in the number of evaluations, and it paved the way for other important algorithms like the factoring algorithm by Peter Shor. And this is one of the main algorithms that actually draw the attention to quantum computing and its capability. Okay, and I'll talk about it in a minute. But there is other remarkable algorithm which is called the Groover algorithm that is basically does quantum search. Okay, so it's a quantum search algorithm, and in fact this particular algorithm which attracts companies like Google into the quantum computing field because basically they saw an opportunity for such quantum search algorithm to search into, you know, unstructured documents that they have. And it took them about 20 years or so in 2019, where they claimed that they reached quantum supremacy. And quantum supremacy is a terminology put by a physicist, which indicate the time where quantum computing outperforms the state-of-the-art classical computer in a particular problem, in a very, you know, like in just a specific problem. And that we reached that in 2019, although it was controversial a little bit because Google claimed that, you know, their quantum computer, the Sycamore, executed the problem that would have taken 10,000 years, I think, 10,000 years in the state-of-the-art classical computer. But then IBM refuted that was saying, you know, that you have basically misconfiguration and it should take about 2.5 days. But anyways, you know, it's quite a difference. But again, quantum computers were able to solve things that classical computers could take quite some time. But the next year, only last year, now the term supremacy was not really. It's kind of was rejected by many scientists, by the community, and now they are using what is called the quantum advantage. And just last year, a Chinese group, they said that they achieved the quantum advantage on a useful problem, the problem called boson sampling. Now, what happens between 1996 since the Shor's algorithm came into surface and current year? There was a lot of development in terms of quantum computing. So in 1982, just a concept, we know just the concept. In 2000, and I think this is a national lab in US, they built what is kind of the first quantum computer, 7 qubits. But now we have, in just 2019, Google, they built their controversial quantum computer with about 72 qubits. So in only 18 years or so, there were a lot of development in terms of engineering and building an actual quantum computer. Now, again, John Priscall, the known physicist, he described this era of quantum computer that we live in these years as the noisy intermediate scale quantum. And his projection that is predicting that within this era, we will be able to build quantum computers in terms of tens, maybe hundreds of qubits, no more than that, but with moderate error rates and limited error correction. And it is estimated that 80% of the instructions and processing of qubits on quantum computing goes only for error detection and correction. So only 20% of actual computing is done. And that is because qubits are fragile, right? And they have a short decoherence time. Basically, they lose their states very fast. And we really want to measure the qubits within, like very, very short time, okay? These are some photos for actual quantum computers in IBM and Rigetti. And see, they always look like this shape, like a cylindrical shape, where at the tip of this structure is the quantum chip that contains the actual qubits. And of course, all these wirings are used for controlling the qubits. And that's why really I made the statement early in the talk where really quantum computers will not be the replacement because of classical computers, because we still need the CPUs and classical computers to control quantum computers. These are the use cases for quantum computing, basically in quantum chemistry, simulation, and quantum machine learning. But the most important application for quantum computing is simulating quantum physics and the quantum phenomena. Okay, and this what made Richard Feynman in 1982 or so to kind of put forward the concept of quantum computing in his seminal paper, Simulating Physics with Computers. Now, if you are wondering how did Deutsch solve that problem, basically by arranging the qubits in certain superposition state and then measure it. Okay, so in a high level, very high level, this is how it looks like using 3 Hadamard gates and some function here, whether it's constant or balanced, we can put it. Now, if we measure this output here and we get a 0, then we know that this function is constant, otherwise it's a balance. Okay, and the art and science of designing quantum algorithm is not an easy task. Again, Scott Aronson say that designing quantum algorithm is like choreographing a pattern of interferences and amplitudes. That's why really it takes a lot of effort to actually design a quantum algorithm. But I think with the sciences is getting a little bit advanced and algorithms are getting easier and easier by the day. Now, another misconception or myth about quantum computing is that it can solve all hard problems, right? But this is not really true, that's not correct, because we still know that there are problems that cannot be solved with quantum computing. But on the other hand, we know of hard problems that can be solved efficiently with a quantum computer. One of them is called Shor's algorithm, which is basically the problem of factorizing a number into its product of primes, right? And again, this is an example of a hybrid algorithm that need to be run, part of it run on the classical computer, classical processor, and part of it need to be run on a quantum processor. Okay. Now, this is what makes organizations and companies a little bit to panic, because if we build a large-scale quantum computer, then most of the crypto scheme that we know of, like RSA and so on, will fail, will be broken. But really, it will take us a little bit, quite of time from now to realize or to build a large-scale quantum computer with about 10,000 qubits that is needed to actually break 128-bit RSA crypto scheme or so. I think I'm a little bit approaching the time, maybe over time actually, but I just would like to quickly go over some important protocol using quantum computing. And this is because of this theorem, no cloning theorem. Basically, it says that you cannot clone a qubit from one place to another. You can only move it. Using this theorem or this result, we can achieve what is called quantum key distribution. And in a nutshell, I will just skip this. Alice and Bob can actually agree on a secret key over unsecure channel, even with the presence of some evil in the middle, like a man in the middle attack. Okay, so we'll still be able to share a secret key only using this quantum key or quantum phenomenon. Okay, and this is a protocol called QK88 or quantum key distribution that makes that has a lot of implication in the cryptography field. So scientists and in terms of cybersecurity, they categorize the field or the efforts into three categories: post-quantum cryptography, right? Quantum enabled, so basically using quantum phenomena in order to quantum inspired in order to improve the cybersecurity of the crypto scheme and so on, and quantum enabled. These are some potential applications of quantum computing in terms of robotic manufacturing to solve some optimization problems, as well as in machine learning. Okay, so basically, they saw that quantum computing has the ability to perform mathematical operations in a very fast, most efficient way. Today in Delft University, they built the first quantum internet out of 4 nodes, basically to safely or to kind of efficiently move 1 qubit or transfer 1 qubit from one location to another. And this will pave the road for, maybe a worldwide quantum communication. In China, they were able to achieve this quantum communication through satellites. These are the big players in the out there, like all giant tech companies like Google, IBM, Microsoft, and some intermediate and small companies. In fact, IBMQ is the leading in that sense. Basically, you can go and try and use one of their quantum computing platforms on the cloud. And you can basically build your own circuits and interact with the qubits. Now, I told you that I'm not going to go too much into the physics. This is the second slide only, just to show you how do we realize, how do qubits look like. There are many ways to realize qubits. One of them is ion traps, NMR, photonics, and the most dominating form of qubits is the superconducting using Josephine junction. Okay, where do computer engineers fit in all this picture? So this is kind of in terms of quantum computing. This is the stack of the efforts, ranging from the quantum chip, from the hardware, all the way to the high level, the quantum algorithms, the machine learning, the application, and so on. In the low level, I see that physics and electrical engineers are taking the lead in terms of the quantum chips and the interface between the quantum and classical, while computer science really work on the kind of the higher level, the programming languages, the algorithms, the maybe building compiler and so on. But really computer engineers are the best ones to kind of fit all the spectrum from the high level all the way to a little bit lower, upper than, you know, the quantum chip and the hardware. Okay. Now, just I think last year or so, the Ministry for Communication and Information Technology released a report about the future of quantum computing in Saudi Arabia. And they kind of have a projection of the effect or the potential of using quantum computing in many fields, including oil and gas, healthcare, financial services, in the next 5 to 10 to 20 plus years. And in that report, they also emphasized on the efforts in Saudi Arabia to kind of not only establish, but also invest in quantum computing talent in terms of creating quantum computing disciplines in universities and basically encouraging R&D initiatives in Saudi Arabia. And that's why KFUPM has the lead in offering two quantum computing programs, one in the professional master and one in the form of concentration area that is open for computer scientists, for computer engineers, for physicists, as well as for electrical engineers. And I think I reached my slides. I hope that you enjoyed this talk and you found that easy to digest, find this quantum computing easy to digest, and I'll be happy to take your questions if you have any.
Okay, thank you, Dr. Muhammad, for the very useful information that you shared with us tonight. We have about 5 minutes for question and answer. So if you have a question, please raise your hand, or you can go ahead and type the question into the chat box. If you have any questions, also those who are on YouTube, you can type your questions into the chat box. So I have a question for you, Dr. Muhammad. So now Google, they have their own quantum computer in production, right?
Right.
So what kind of application they are running or they are trying on these quantum computers?
So far, no useful applications. And it's just, you know, kind of, like it's a race between those big companies like Google, IBM, Microsoft. Everyone want to take the lead. But so far, there is no, as far as I know, there is no useful application. However, there is one leading company called D-Wave. Okay, they took it. So the application or these platforms, quantum computing platforms by Google, Apple, and Google, Microsoft, and so on, they're called general purpose platforms. But on the other hand, D-Wave, they took another approach. They call it specific domain, right? So they build their quantum computing platforms on what is called quantum annealing platform. Basically, quantum annealing is kind of the quantum version of what is called simulated annealing, right? So it is useful. They found that it is actually useful to solve large-scale optimization problems. And that is actually, D-Waves are actually commercially, you can actually buy it. So it's available commercially. And there are some companies like, I think Volkswagen, some banks, they are using it effectively to solve particular form of optimization problems. But
okay.
I'm not aware of any useful applications for Google and IBM and so on.
Okay, so I have a question from the chat here from Mohammed Al-Alayan. Shouldn't light photons be easier for trials, qubits application?
Okay, good question. So as I said, there are many forms of qubits. It turns out photons are good when we want to communicate. So it's good for actually transferring qubits from one place to another because of the nature of photons. However, capturing it and processing it is not an easy task. And they found that superconductors are the best are the best form of qubits.
Okay.
In fact, for communication, we use photons. For communication, we use photons. For computation, we use form of supercomputers.
Okay. Okay. Thank you, Ghaida, for your complimentary comment and continuous support. Also, thank you, Khalid, for your complimentary comment. Khalid has also a question. He's saying that, Dr. Muhammad, can you please elaborate more on the implication of quantum computing on cybersecurity? So as if he's asking about, well, do we still have a role to play as a cybersecurity specialist when quantum computers become a reality?
Well, good question. Yes, we still have, you know, have key role in that. But that's a long. I don't have, you know, like a direct answer to that. But what I can say is that, you see, it is tricky, you know, like because of one thing, that if we were able to realize a quantum computer at a large scale that can break, let's say, used RSA or like any crypto systems like integer factorization based on discrete log based, then we can not only break confidential the secrecy of confidential documents today, but also retrospectively, like, you know, like all documents that let's say adversary captured and we're able to break it.
So, but we're still like away from the 10,000 qubits.
Yes,
like
yes.
So we are still in business, like as far as cybersecurity is concerned.
We're still in business, but I think the ones that we will be really in business are I would call it post-quantum cybersecurity. Basically using, you know.
Can you explain this concept, Doctor? What do you mean by post-quantum cybersecurity?
Good. Okay. So as you know, like for example, cryptography, they are based on some computationally hard problems. For example, factorization, like discrete log, and so on. And that's basically the basis of RSA. Now, if we were using Shor's algorithm, if we were able to break or factorize numbers into its prime numbers, then we can basically break this crypto scheme. Now, cryptographers are looking for other ways, like lattice-based, code-based, hash-based, and so on, that we still don't know an algorithm that even at the quantum side that can break it. Okay, so that's what I mean by post-quantum algorithm. Basically, looking for difficult problems that we still quantum computers cannot break. Okay, and based our let's say cybersecurity on those problems.
Okay, so I'll take a question from YouTube. So there is a question from Faris Al-Ghamdi. When do you think quantum computer will be available for ordinary customers? I heard that there is a company in Canada where they have built like consumer level quantum computer, like for about $5,000. Is that true?
Well, I'm not sure if it's in Canada or in China. They have, believe it or not, they have a portable quantum computer, like a laptop.
Ah, okay.
That contains 2 qubits only. It's unused. It's useless. But
is it running Windows or Linux?
Well, very, you know, what was that? The old 1990. No, but I think no, not anytime soon. Maybe, what I would say the first real applications are going to be, you know, just like the early ages of computers, the ENIAC and the mainframes. They were only affordable by you know, enterprises and big organizations. So that's the way I see it, at least for the next 10 to 15 years. But okay. I don't see it anytime soon.
Right. We have a question here. MashaAllah, tabarakallah. Questions are, so keep them coming. Okay. We're going to like extend the time a little bit. Okay. So question that says from Salih Al-Ghamdi, would you please explain the other 2 categories, quantum inspired and quantum enabled?
Okay. So as I mentioned, post-quantum is looking for to base cryptography on concepts or in problems that are difficult. We don't have an algorithm even in the quantum computing world to solve it. Quantum inspired is to use quantum phenomena to solve or to support our cryptographic and cybersecurity problems. For example, one of the main problems in cybersecurity or cryptography is random number generation. you know, and we don't really have truly random number generators. We have pseudo-random number generators. But if we were able to, you know, exploit superposition and measurement in a way, we can actually produce or generate truly random number generator physically using physics, right? And basically, the way we do it is we take a qubit, put it in a Hadamard gate, in a superposition using Hadamard gate, and then measure it. The measurement will have a 50-50% chance of getting a 0 and a 1, and that is purely, you know, purely natural. That's the way I see it. And there are so many other techniques exploiting quantum physics. The other one is enabled is now IBM Q is available on the cloud, right? Now suppose that we have they built up a large scale quantum computer, which is again in the cloud, and we want to communicate our data to the cloud, right? But again, you know, because of the confidentiality and so on, we want this interaction with the cloud to be, again, secure, to preserve the confidentiality of our data. So the question is, how can we enable secure communication of quantum data, of qubits, between our side and the platforms of the cloud?
Okay. Right. We have a question here from Muhammad Al-Sayyari. To the best of your knowledge, Dr. Muhammad, are you aware of any adaptation or deployment of quantum computer in Saudi Arabia in both industry and universities?
Good question. I'm not really aware personally, but I've been in contact with few people. They have efforts, and unfortunately, it's confidential. So that I'm not, you know, I don't know the details of that. But in fact, there is an interest, a good interest, but I don't know like what is the extent of whether we have you know real quantum computers or not. I don't know.
Okay, question from YouTube: would modular arithmetic be adapted to the quantum computing algorithm for cybersecurity?
So what do you mean by modular arithmetic? Like
I think he means like standard algorithm. Would they be adapted to quantum computing?
Good question.
For cybersecurity?
Right. The short answer is quantum computers can do anything that classical computer can do. So if you want to do modular arithmetic in quantum computing, you still can do that.
Okay. We have a question from Aqil. Two more questions, Dr. Muhammad. Do we have real use right now for quantum computing, or still like it's just theoretical in the lab?
Yes, good question. Yes, as I mentioned earlier, D-Wave is the leading company in producing or in commercial quantum computers. They have, just 2 years ago, they released the D-Wave 2000Q, which has about 2,000 qubits. And I know, as I mentioned, at least 2 to 3 companies from the auto industry, from the banking industry, from logistics industry that are actually using those D-Waves to solve certain optimization problems in their domains.
Okay.
So practical use.
Yeah. Khalid Al-Zahrani, I'm sorry, I did not see you. Khalid, go ahead, please. Use the mic. Khalid, go ahead. Sorry والله.
السلام عليكم.
السلام ورحمة الله. حياك الله.
الله يعطيكم العافية. شكرا دكتور for the excellent session. I have a quick session. If I am a company and I want to benefit from quantum computing, in one of your slides you listed the number of companies and some. What would be the criteria I should be looking for to select the right partner for me?
Right, good question. So it depends on what you want exactly. Any other problem, right? So if you are looking for a particular problem in a domain where, for example, if you are looking for if you are let's say in logistics domain or industry, and you want to find a solution for the best route for your trucks and so on, then probably D-Wave is the current or the only available solution. That I know of. Maybe there are other solutions, but I know that D-Wave has this kind of. Now most of the interest from these big companies is because they want to have the lead in this world or in this technology. Okay. So I don't really have a short answer to that, but probably is depending on your requirement. What do you really need? If you
but is any of these company providing quantum computing as a cloud service, not the infrastructure, I mean the services on top of the infrastructure? For example, if you're talking about logistics, do they provide services on top of the quantum infrastructure?
Yes, yes, there are. So there are a number of them. And I'm aware of, as I mentioned, D-Wave that provide the structure. Atos, for example, is that they provide kind of software. And the rest I just know by the name, but I don't know really what is their, like service model really. But there are some companies that provide quantum computing as a service, but also not as infrastructure, but also as a service.
Okay.
For example, you need a solution for a particular problem. They run it on a quantum computer and they provide it.
Okay. Khalid Zahrani, any follow-up question?
Yes, if you allow me, and I
yes,
just wanted
go ahead,
to if I wanted to understand, again, back to my first question, like we know IBM, Google, and Microsoft, and every one of them is a claim that they have some lead on quantum computing. Is it smart for a company to establish multiple relation or focus on a single partner? Or
yes, I see. That's a very good question also, because at this point, each company is building, their own technology, their own stack. Looking at this stack particularly, so IBM has its own stack, while Google has its own stack, and they are different. When I say stack, it goes from the interface between the classical and the quantum, to the instruction set, to the compiler, to the programming language itself. Okay, so at this point, I don't see any. Well, from the public information that we have, I don't see any advantage or any. So they are all equivalent. That's what I wanted to say. Maybe there are some kind of confidential information that we don't know of. Obviously, there must be up. But I don't know. I think it might be smart to have maybe multiple collaboration with multiple partners, or collaboration with multiple partners, in order to see like where is it. But nevertheless, they are all converging to the same technology, the same stack, because they are all using superconducting qubits, and the physics and the engineers in cooling and in realizing a qubit and measuring with the qubit is basically they all go with the superconducting qubits. Now, one thing, but I mean, maybe I'm giving you a wrong answer. One thing that I see is really important to look at is what is called the error correction codes or ECC for the quantum computers. Now, I believe this is where the companies will have an edge over the others. Is, let's say, how many operations, effective operations, or percentage of operation that actually does effective processing of qubits, rather than wasting it in error correction and recovery. Okay, and I don't know of any company that is taking the lead.
Okay, Khalid, I would encourage you to reach out to Dr. Filimban. I have posted his email on the chat. Also, I want to remind everybody that Dr. Filimban is the director of the newly established Center on Intelligent Secure Systems, and quantum computing is one of the major topics on their research agenda. So we have a comment here from Al-Alayan. It's very interesting that quantum computing is easier to look at as a mathematical probability. I think he means that the underlying mathematics for reasoning about quantum computing is probabilistic. Thank you for that. If there is a way to superimpose such to build, I think you can read the question from the chat, QCMB to build smaller machine learning microsystem to smooth out uncertainty engineering. So it seems that he's asking about, do you think quantum computer will play a role in the area of machine learning?
Yes, definitely. Definitely. And I'll give you one example, okay? Because, you know, at machine learning, even in deep learning, they are basically mathematical operations, right? Basically arithmetic operations, like inner products and so on. Once we talk about inner products, once we talk about matrices and columns and tensor product, this is where quantum computing excels. And that's why we turn around, if we're able to reduce any machine learning algorithm into basic mathematical operations, then we can utilize quantum computing. And in fact, there are some efforts along that route for deep learning, for support vector machine and so on.
Okay, last comment and question. Are we expecting future compatibility issues for running quantum computing program on various architecture or stacks developed by different companies at operating system level, or there is already a standardized operating system that supports all the various QC platforms? Wow, that is very specific.
Yes, very, very good question. There are no standardized so far. That's why every company building their own stacks, and even, you know, like, you know, for example, Intel has its own instruction set.
AMD?
Yeah, they have instruction set basically, right? Yeah. So similarly, so Google has its own instruction set, quantum instruction set. IBM, they have their own, and they all differ in the basic gates, the basic quantum gates that they support. Okay, so yes, there might be, although the technology is converging in terms of cooling down the qubits and dealing with qubits, but I see that the stack, the software stack at least, will not have a standard. Each one will reach to their own optimized stack based on their needs.
Okay, so we'll take one more question, Dr. Muhammad, if you allow us, from Muhammad al-Sayyari. Muhammad, go ahead.
Salam alaikum. Thanks, Dr. Muhammad, for this great presentation. My comment earlier was about when you mentioned that it's better not to engage with one only quantum hardware like IBM alone or D-Wave. It's rather to maybe check your use cases and see what is best fits of the quantum. Here comes the software and consultants to the right of the screen, like OneQubit and others, in fact, like Zapata and Cambridge and others. They claim that they have their hub or their system, that they have access to multiple quantum hardware like IBM and D-Wave and others. So with this result, do you recommend like having partnership with those ones instead of going directly to a particular quantum company like IBM alone or D-Wave?
Okay, good question. To tell the truth, this question is beyond my knowledge, because I tend to see quantum computer from kind of science and education, but I never tapped into the business of having quantum computing, or like providing quantum computers. I don't know. The short answer to your question is I don't know, but I would like to.
But I think, Abu Yusuf, we should mention our partnership with Dr. Siddiqui through the physics department.
Right.
And every year we host him, and he can we organize events, and they can attend and talk with him about, and because he's very familiar with what's happening in the US market. So do you want to comment on that?
Yes, definitely. Yeah. So thank you for reminding me. Yes. So we have actually kind of research collaboration. And it's more than research, actually, with Professor Irfan Siddiqui from Berkeley, where he definitely has access to a wider range or more, let's say, players in the quantum computing field or community. So maybe, I don't know, maybe if we can consult Dr. Irfan to give us a kind of maybe a better answer for that. Yes, we can actually connect you with that, and I would be happy to follow up on your question and do my maybe homework, and then
Sure, Doctor. I got the chance to talk to you earlier today. Yes, and for sure we agreed we will have inshallah follow up.
Inshallah, definitely.
Okay, so thank you, Dr. Muhammad. Thank you, everyone, for this interesting discussion. and we look forward to see you again next week with another seminar. Thank you Dr. Filimban, and تمسون على خير جميعا. السلام عليكم ورحمة الله.
يعطيك العافية دكتور يحيى.
السلام عليكم.